So I'm Rosemary Wise of the Johns Hopkins University, and it gives me great pleasure to be the moderator of the Aspen Center for Physics. I'm so excited. Aspen Center for Physics Colloquium today, live from the Aspen Center for Physics in front of a live audience. I sound like a late night show host. I and today's speaker, Professor Robyn Sanderson, are here in Aspen as part of one of the two workshops going on in person right now. It's wonderful to be here, to be actually talking to people face to face, enjoying talking science, enjoying Aspen. The science that we're talking about, getting really excited about, is to do with galactic archaeology, which is using the motions, chemistry, ages of stars in our galaxy to infer how galaxies formed and evolved. Professor Sanderson is an expert in particularly how dark matter sculpts how galaxies form and evolve. And what she's going to be telling us today is dynamical tests of dark matter in the Milky Way. So Robyn, Professor Sanderson, did her PhD with Ed Bertschinger at MIT on investigations of indirect detection of various kinds of dark matter. She then went to the Kapteyn Institute in Groningen, excuse my, my Dutch, where she got perhaps more involved with connecting observations to dark matter. And then she got an NSF fellowship, and she moved to Columbia and then to Caltech, got really involved in confronting simulations of how galaxies form with observations. And that's what this workshop's all about. We're really excited about it. Robyn, now turn it over to you. Tell us all about how we find out about that matter. Oh, and I almost forgot questions. We're going to leave questions till the end. And we're going to have remote with priority since Robyn is here for the next couple of weeks. When you're here in Aspen, you can talk to her afterwards. Please, remote, put your hand up and then we'll call on you at the end. Thank you. Robyn, take it away.
Thank you, Rosie. And thank you very much for the organizers for giving me this opportunity. I'd also like to thank, and I know they're probably watching out there, my husband and his parents who are watching my 1.5-year-old and making it possible for me to be here. So today I'm going to talk about some work that we've done in my group recently to try to construct new dynamical tests of dark matter using information about our own galaxy, the Milky Way. This work would not be possible without the contributions of the Gaia survey, which is an astrometric survey on a space-based satellite that you see there. And this is really the first large-scale phase space survey of the Milky Way, meaning it measures both the positions and the velocities of a lot of galactic stars. There we go. So for those of you that don't spend a lot of time thinking about this, I thought I'd just clarify what exactly it is that Gaia is doing. So when you go out to measure the three-dimensional position and velocity of a star, you have to measure 6 numbers. 3 of them are positions. And so in practice, what you do is you measure the distance to the star and then its angular position on the sky. And we use a technique called parallax, or Gaia does, to measure the distances. I'll get to that in a minute. And then to measure the velocity, you measure the line of sight velocity using the Doppler shift of spectral lines in the stellar spectrum. And then you measure the change in the position of the star on the sky over time, and that gives you 2 angular velocities. And you use the distance measurement to convert those to physical space velocities. So Gaia measures all but the line of sight velocity for every star in its catalog, and that's a lot of stars, as you'll see momentarily. And for a subset of the brighter ones, it also measures the line of sight Doppler shift. So the way that it does that is an elaboration on the following technique. And I will give you an example using Proxima Centauri, which is the closest star to the sun, and therefore the one with the largest signal, because all of these signals decrease as 1 over distance, given that they're angular measurements. So basically what you do is you take a picture of the star and then you wait a long time, and then you take another picture and then you wait another long time, and then you do this several times, and then you line up all the pictures using stars that are, are far more distant in the background. And then you get an apparent motion of this star across the frame, as you can see back here. And if you were to zoom in on that, you'd see that the motion has two components. One is the intrinsic velocity, which sort of brings it across the frame. And then the other is this sort of loopy motion, and that's the parallax. That's the reflex apparent motion induced by the Earth's motion around the sun. So it has a period of 1 year, which is why Gaia, having been operating now for almost 5 years, is starting to really get into the meat of its parallax measurements, since you have to have more than a year's worth of data before you can even disentangle these two signals. So this is what Gaia does for basically every star in its catalog. And just to give you an idea of how hard this is, so this is the nearest star with the largest signal. It's got a parallax of about 3/4 of an arc second. An arc second is 3.3 thousandths of a degree. And typically, stars in the Milky Way have parallaxes of milli arc seconds to micro arc seconds. And their proper motions are milli to micro arc seconds per year. So Gaia is doing an amazing thing by measuring these tiny angles so precisely. And it does it for like a bazillion stars. So this is a distribution of the stars that Gaia sees in their apparent brightness. So this side is bright, this side is faint. And this blue curve up here is all the stars that have 5 of their 6 phase-space coordinates measured together by Gaia. So that's the astrometry. And then this subsample in green is the ones that also have their line of sight velocities measured. And those stars constitute a complete phase-space catalog of our galaxy for the first time pretty much in history. So I want to go back to this image that I showed you earlier, because it's not your ordinary picture. It's actually made of the light that Gaia observes from all 1.8 billion stars, which is about 1% of all the stars in the galaxy. And so what they do is but Gaia sees these stars in several different color bands. And this image is constructed by taking all the stars that fall in a particular pixel, which are so tiny you can't see them, and adding up the light in the different bands and assigning them to the RGB channels. So there's all 1.8 billion stars went into the manufacturing of this image. And I think that's just amazing. So this gives us a window that we've never had before in our galaxy. Gaia is literally 1,000 times better in every regard than the information we had like this before Gaia DR2 came out. So this tiny little circle around the sun here, that's the extent of the previous Gaia-like substance that we had called Parcos. Gaia sees to the same accuracy in this volume for parallaxes, and to this volume for proper motions. And this data set it's not any exaggeration to say, completely transformed our view of the galaxy in the last 3 years. So what does this have to do with dark matter? The Milky Way dynamics provides multiple different laboratories for studying dark matter. So this is an image from a simulation of a Milky Way-like galaxy. So I can show you the dark matter as well as the stars. And in the main galaxy, which is the concentration of stars right in the middle there, you can get, by examining the dynamics, a diagnostic of the interplay between dark matter and standard model matter. So I'll call that baryons for this talk, since that's how astronomers think about it. This also gives us a connection with the dark matter distribution in the local solar volume, which constrains the direct detection experiment rates that people derive. And then you see, let me get my pointer on the right screen here. And then you see these little tiny blobs of stars. Those are satellite galaxies orbiting the main galaxy. We see those around the Milky Way as well. And those are essentially just smaller galaxies on different mass scales, and they have a different balance between dark matter and baryons. So that allows us to test scaling relations and theories of how the two substances affect each other over time. These satellites are also generally pretty good candidates for indirect detection of dark matter. And finally, you'll notice that the stars are definitely a biased tracer of the dark matter. And in fact, in the middle here, there's sort of 50-50 stars and dark matter in terms of mass, but out here, it's mostly dark matter. And so out there, we have a chance to sort of disentangle stuff that's going on in the baryonic component of the galaxy from stuff that's happening with the dark matter. And a key ingredient in doing that are these long tails of stars that you see here, which used to be satellite galaxies, but have been ripped apart by the tidal forces of the main galaxy. And these are very sensitive gravitational antennae that tell us especially about the shape and the small scale structure of dark matter in a region where it's more or less unaffected by the evolution of the central galaxy. So how do we connect these things together? So I give you a clue on the last slide. But in order to make predictions for what the dark matter distribution should look like around a galaxy in a given dark matter model, you initially have a big initial value problem. And we know the initial conditions. There they are. This is the map of the temperature fluctuations in the cosmic microwave background. These translate to density fluctuations. The cross section that you propose for your dark matter theory sets the amount of dark matter that you make. This is a simple example from a cold dark matter paradigm. And then you zoom in on a little section of these, you populate the density distribution with particles that represent the mass. You use a computer to add gravity and time, and you get a prediction for what dark matter should look like on the scale of the Milky Way, which is shown here. So, like I said, the mass and the cross-section determine how much you get. The minimum mass of these little tiny blobs of dark matter that you see here are set by the primordial temperature and the production mechanism of dark matter in the early universe. Until recently, the working assumption, as is the case here, was always that dark matter was a collisionless substance, according to the sort of vanilla lambda CDM model. And that essentially means that the dark matter cross-section is only relevant in the early universe. However, recently, people have started to play this game where they've relaxed this assumption. And you can see that there are differences in visibly in the prediction between these different models of dark matter on galaxy scales. And so the game is then we have to somehow compare what we observe in the Milky Way's stars and gas to the dark matter distributions predicted by these simulations by inferring where the dark matter is from the things we can see, and thereby somehow constrain and rule out all these different models. All right, so the wrinkle here is that sometimes the observational comparisons that we make can have multiple ways of reconciling. So I'm going to use a relatively old problem here to illustrate this, called the missing satellites problem, which is essentially the fact that if you go back to that slide, you saw like tons and tons of little lumps of dark matter that CDM predicts should be around, but we don't see that many satellite galaxies around the Milky Way. We see like, 50 or something. And so you can either get rid of all those low mass dark matter halos by introducing a higher primordial temperature for the dark matter, which is what you see here. So this is the number of halos you get essentially at a given mass in your theory. And this is the collisionless model. This is if you have a warmer initial temperature, so it washes out the smaller scale structure. And that can bring you back into reconciliation with how many actual satellite galaxies we see around the Milky Way. Or you can add to your dark matter only simulation processes that affect the gas and stars in the galaxy, such as reionization and feedback, whereby things like supernovae and stellar winds dump energy back into the gas. This suppresses star formation preferentially in smaller dark matter halos because their potentials are shallower and can hold on to the matter less efficiently. And it has the same effect of bringing the number of predicted satellite galaxies as a function of their mass back in line with what we observe around our galaxy. And that should say M31 or Andromeda. So you can either fix this problem by manipulating your dark matter model or manipulating your standard model physics that you include in your simulation when you're making the prediction. And this is a little bit of a facile example because actually, you have both going on. But I use it to make the point that the process of galaxy formation links the dark sector and the standard model sector primarily through gravity. And so a big question that I am trying to tackle, and I'm not the only one, is how we disentangle new physics like what dark matter is from poorly understood physics, like the links between how dark matter halos are structured and how the galaxies form inside them. And both of these sides of this problem are interesting, sometimes to different people. I find them both fascinating. But I'll hope to convince you in this talk that the type of simulations that we are capable of doing now that evolve a Milky Way-like system on a cosmological background are key to interpreting all these measurements that we see from Gaia and from other sources, because they incorporate both sides of this issue. So on the theory side, a key tool to answer these questions is to simulate all these nonlinear processes involved in galaxy formation in a realistic way. And in this talk, I'm going to show a lot of results from this particular suite of simulations of Milky-Way-mass systems, include cosmological initial conditions, dark matter, baryonic matter, state-of-the-art stellar feedback models, which are recipes for how the stars deposit energy, momentum, and chemical elements back into the gas of the galaxy to form future generations of stars or not. Among other things, these simulations produce galaxies with thin stellar disks like we see in the Milky Way. And they end up having an appropriate number of satellite galaxies of the right sort of sizes and velocity dispersions and things like that that are important for dynamics. And they have also a stellar halo made of tidal streams. And this is basically the first time that people have been able to resolve the creation of these things self-consistently in a cosmological baryonic simulation. And finally, after hard work by many people over decades, these kinds of simulations are beginning to convincingly resemble our own galaxy. So if people who study the Milky Way will know the answer to this, but one of these is the real Milky Way and one of them is a simulated galaxy. So we're starting to at least be able to convince ourselves that we have some capability of connecting the physics in our simulations to observations. And I'll talk more about that. We also need to use this type of simulations because the galaxy is definitely not a static system. So you can see here a movie of one of these simulated Milky Ways assembling itself over time. There's all kinds of stuff happening. There's mergers, there's like gas blowing out into the outer halo. All this stuff is going on, and all of these disequilibria pose challenges for the dynamical models that we use to infer the dark matter distribution. And this is a big theme of discoveries that have been made so far with Gaia. Gaia has established a new picture of our galaxy as a system in disequilibrium. Our disk is continually bombarded by satellites that lead to asymmetries like this one seen in the gas disk here, or non-equilibrium populations like the famous phase space spiral. This is not a configuration of positions and velocities of stars that you would get if the Milky Way were in equilibrium nearby. And we've even detected satellites that are in a very good position to perturb the outer disk, and hints that existing known galaxies may be perturbing the inner disk. The point is that these are both challenges to sort of the status quo pre-Gaia, which was to assume that our stars are in equilibrium, and also opportunities to create some new paradigms that could possibly make better tests of dark matter. And they're fundamentally cosmological in many cases, right? This has to do with interactions between our galaxy and its satellite population. And so you need a cosmological background to understand what to expect from this situation. So Gaia's dynamical snapshot lets us model the total mass distribution, assuming we can confront and successfully resolve all of these things. But it's also a survey of the galaxy stars, and that helps us figure out what fraction of the mass in the galaxy's disk is luminous versus dark. So there have been many efforts to map the distribution of the Milky Way in dark matter using the Gaia data. And these efforts are then connected in turn to particle models of dark matter through the kinds of simulations that I've been talking about. So today I'm going to describe a few scenarios that my research group and I are involved in. And they're listed here. If you want to know about the first one, you can ask me afterward. I'm going to focus on the last three. Oh, or not. My slides say otherwise. Okay. So let's talk about the total mass of the Milky Way, because this is really sort of the zeroth order thing that you think we should be able to do. This is a very important parameter for a number of reasons. One is just that it directly normalizes predictions for the number of substructures in the galactic halo. So if you have this sort of, this is a theoretical picture of the expected number of substructures of a given mass that we have given a main halo of different sizes. So this solid line down here is if you have a mass of 10 to the 12 solar masses in your main galaxy. This dashed line here is 10 to the 13. That's 10 times what we think the Milky Way is. And a factor of 10 uncertainty in the mass of your host galaxy is directly proportional to the uncertainty in the number of subhalos you expect at a fixed mass. So how well do we know this for the Milky Way? So Gaia has had a big impact here, and people have come to basically a consensus on the mass and shape of the Milky Way in its inner 20 kiloparsecs. There. So that's less than a tenth of what we expect the radius of the dark matter halo to be. And that's not surprising because that's where we have a lot of data, right? That's where all the stars are, and that's where Gaia is observing. If you look outside that region, so you can see, look, there's all these people that did different estimates that all agree right here. All of these other points are other measurements of the Milky Way's mass at different radii by a number of different methods. So most of them out here use either a description of different point tracers in orbit around the galaxy, like globular clusters or satellite galaxies, or they construct models of single tidal streams, disrupted galaxies. So the tidal streams should, in principle, provide us with extra sensitivity to the shape of the galaxy and to the mass profile at large distances, because essentially once tides destroy it, those stars from that galaxy are now just test particles that are all on similar but not quite the same orbit. However, what we've found, what numerous groups have found, is that if you construct a model of only one stream at a time, then they're subject to quite a lot of bias. So we can do better now that we have Gaia, because not only do we see stars in many different streams with Gaia, but we have 6-dimensional information about their stars' orbits. So we can really unleash the full power of Hamiltonian dynamics. And in particular, we can use the natural framework for bound orbits, which is actions and angles. So for those of you that haven't cracked your classical mechanics textbook in a while, if you have the momenta or velocities and positions of stars, you can make a canonical transformation, so it preserves things like conservation of angular momentum, to this framework called actions J and angles theta. This is how you calculate the actions, and then the conjugate variables are now the angles, which evolve linearly with time. So the key here is that you have to make some assumption about the coordinate system in which your potential is separable. That means you're assuming something about its symmetry, and we'll get back to that later. But here I'm going to show you a little movie with a toy model of some streams disrupting in a fake galaxy. Over here, you see what's happening to them in position. This panel shows you one of the actions versus its conjugate angle, and down here is what's happening in 2 of the 3 actions in this system. And I've put in several streams on different orbits, and you can see the positions of these little blobs correspond to different orbits in this, in different orbital shapes. And then the sizes tell you something about the initial mass of the dwarf galaxy they came from, because that scales with the total phase-space volume occupied by the stars. So the other thing you'll notice here is that they don't occupy all of this panel, but they stay sort of confined to these simple little blobs. And that's because all of these streams are from galaxies that are much smaller than the Milky Way. So since this is the case, if you have a bunch of streams that are spread out all over the sky like this, if you know the potential and can calculate their actions, you'll find that they preserve these little clumps. So these are a little less well organized and a little bit more structure in the clumps than in the toy model I showed you previously, because this is a cosmological simulation. It's relief that the Ansatz still works here. If you don't know the potential very well, or if you guess wrong, you don't get clustering. And this is a model that's sort of 1 sigma in some sense away from our best fit for this simulation. So what I and my group have been working on is to quantify this using a statistical measure of the clustering or information in the action space of stars. And then you can use that as the figure of merit to find the best fit potential. And that has the advantage that you don't actually need to know what color, so to speak, each of these dots are. You can quantify the whole distribution's clustering statistically. And since Gaia doesn't tell us which stars belong to which stream, that's a useful property. So in case you're wondering, if we test this on this simulation, the red line is our best fit using action space clustering, and the black line is the binned mass in the actual simulation. So we've started to apply this to data on real streams now, and we're baby stepping out because Gaia's reach is still a little bit limited in terms of its radial velocities. But this is work by Stella Rhino, who's a finishing PhD student at Leiden in collaboration with me and her advisor, Eleanor Rossi. And you can see here that if we use all 4 of these streams together, we get this crazy constraint here. But if we leave out the Helmy stream for reasons that you can ask me about later, we get these constraints in the pink curve. These other things listed down here are all other measurements of the circular velocity, which is proportional to the square root of the mass, using completely different techniques than this. And so we're getting something that is reassuringly close, and we're headed towards using stars at larger distances in a lot more streams to extend this technique. One thing you can notice is that there's a significant bias in some of the individual fits, which are these points in different colors. And that's what I was talking about earlier. Particularly GD1 has a troubling amount of bias. We are working to understand this now using streams and cosmological simulations, and we think that it's closely tied to the orbital phase of the stars in the stream. So that's whether they're near closest approach, at their furthest distance, or somewhere in between, affects the power that an individual stream has to constrain the potential. All right, so if we can constrain the total mass, we can also start asking questions about the shape of the Milky Way. And by shape, I mean the ratio of the symmetry axes of the potential, or the approximate symmetry axes, rather than the density profile. So this is how flattened and triaxial the halo is. And the shape carries information about dark matter self-interactions, in particular the impact of the crosstalk between baryons and dark matter. So Gaia has enabled a lot more attempts to measure the Milky Way shape. Since Gaia DR2 is everything above this red line in just 4 years, and these other measurements span like 18 years. And if you plot all of the stuff in this table, this is the sort of thing that you get. And we can compare this to some of these cosmological simulations. So the black band here is cold dark matter only simulations. They predict flat halos that are much flatter than what we observe in the Milky Way. When you add a disk growing self-consistently in the middle, you get, this red thing, or this red band over many halos. So that's a little rounder, that's good, but not quite as round as what we measure. So people theorized maybe self-interactions in the near universe, so in the recent universe, could help in reconciling this apparent discrepancy. So this blue line, the solid blue line here, is a simulation where they took a self-interacting dark matter only cosmological simulation, put an analytic disk in the middle, and grew it inside the galaxy over time. So it predicts it should be a little bit rounder than your average CDM halo. So maybe this will help, but we really need to account properly for the baryonic effects here, because we already know that if you simulate the same system without and with a galaxy growing in the middle, the one with the galaxy growing will be a lot rounder, especially in the middle. And you can just see that right from these images. And this is because the two exchange information through gravity. And the processes by which this happens and the extent to which this happens depends on the dark matter's ability to transport energy and angular momentum in the halo. So it should, in fact, be sensitive to the self-interaction cross-section of the dark matter. So cold dark matter is extremely inefficient at transporting energy and angular momentum because it's totally collisionless. Self-interactions can make it more efficient. And so you might expect the halos to be a little flatter in SIDM than in CDM, just based visually on this, but in a different direction than when you leave the dark matter out altogether, in which case the axes of symmetry are set by the inflow of matter onto the halo from the cosmological filaments. So once you account for the growth of the disk through a full baryonic treatment in an SIDM halo with the same initial conditions as a cold dark matter system, you actually find that it's hard to distinguish on this plot. All of these are the shape profiles of different dark matter models, all these dark blue lines. The solid ones are in fact the CDM ones, and the SIDM ones are all the dashed and dot dashed lines and whatever, but they basically look pretty much the same. So we can't make rounder halos using SIDM. However, what we found when we started to look more deeply into this is that in an SIDM model, the size of the region where you expect the collisions to matter varies from smaller than the size of the typical galactic disk for stuff around 1 centimeter squared per gram cross section to larger than the typical size of the disk. And this means that the region where the shape of the galaxy's overall mass distribution is affected by the disk is probably correlated with the size of the disk for a cold dark matter model, but with the size of this local collision region in an SIDM model. And so now we're exploring ways to use this to try and probe or rule out particular cross sections. So stay tuned. All right, so going back to this though, why the heck are all these shape estimates all over the map here? I thought we had all this data from Gaia. We should be able to do a good job with these models now. But the Milky Way is merging with the Large and Small Magellanic Clouds. And recent work has shown that these are pretty big compared to the Milky Way. Maybe not now, but originally were probably about the Large Magellanic Cloud before merging with our galaxy likely had a halo that was about 1/10 of the mass of the Milky Ways. So this system now is found at about 50 kiloparsecs, which is right here. And so it's very plausible that it's interfering with our ability to measure the shape of the galaxy because most of the models that I show you here don't have a separate piece of their model for the LMC. And recent work has in fact shown that ignoring the presence of the LMC really biases your estimates of the shape. This is work by Eugene Vasilev and company. And it messes up a lot more than that. So it also can complicate the standard assumptions that we make about the Milky Way's potential, about its dynamics, and especially in the region which we hoped was just dark matter dominated and would be a little bit easier to deal with. So in particular, most of the models that people construct of the Milky Way's mass distribution are either have a spherical or an axisymmetric halo and ignore the LMC, especially when looking at the shape. And when we want to calculate actions, often we assume an axisymmetric potential just because it's easier to deal with. And so in my group, we've been looking at how far we can push these oversimplifications before they really break down. So here what you see are two sets of tidal streams, one set in the halo of a galaxy that has no major merger or even sort of LMC mass merger. Nothing's going on there. And then down here is a simulation where you have a merger with an SMC mass galaxy. So it's a little smaller than the Large Magellanic Cloud. So what we expect is that the actions should be adiabatic. These clumps should pretty much stay in the same place and the same size as time goes on, as long as we have a decent model of the potential with which to calculate them. Here we used a low order multipolar expansion in an axisymmetric framework fitted directly to the simulated galaxy to calculate the actions. So this is what it looks like just before the merger in the bottom panel. Keep an eye on this gray blob here. This is one tidal stream. During the merger down here, you see that this thing starts to get all funky shaped, definitely not the same as it beforehand. Up here, there's no merger, obviously, so this one is staying more or less the same. And then after the merger, this guy ends up way over here. So what this is telling you is that it's now in a different place in our approximate action space, which would imply a completely different orbit for its stars, yet it's still kind of coherent in this space, although a little bit fuzzier than it used to be. And so this is according to our oversimplified model. So you can see that it's starting to break down in the presence of a merger that's not even as big as the LMC. This is work by my grad student, Arpit Arora, who's entering his 3rd year. The interaction with the LMC also predicts a certain dark matter response due to dynamical friction. You can see the examples here not only does it leave its dark matter as it's tidally stripped in the Milky Way's halo, but it also creates a wake by dragging dark matter behind it due to its gravity. And this effect is very likely to be model specific to the type of dark matter for the same reasons that I was talking about before. And so this provides potentially a new opportunity to test dark matter models by understanding how dynamical friction works and how wakes are produced in these different cases. So there's some evidence that now that we see, very recent evidence, this is from last month or 2 months ago, that we see this wake happening in density variations in the stellar halo. And there's also the potential to detect this effect in the velocities of stars in the halo as well by calculating essentially the spherical harmonic components of the different velocities of the stars. This is work by Emily Cunningham, who's a Flatiron fellow at CCA and works closely with my group. This was super fun. All right, so the shape of the galaxy is definitely still a work in progress, but has a rich set of possibilities for probing dark matter in the future. The last thing that I'll talk about is how we can constrain the substructure of dark matter in our galaxy. And this is generally sensitive to things like the primordial temperature of dark matter and the nature of dark matter interactions, both in the early universe and in the present day. So going back to this slide, you can see that if you increase the temperature, you wash out small scale structure. This type of dark matter creates a completely different spectrum of substructure than the others because it's based on a very low mass axion. And so some of the substructure that you get is sort of like interference patterns of the dark matter, since it has a de Broglie wavelength. It's like galaxy scale. It's pretty crazy. Anyway, so going back to the missing satellites problem, one of the most fundamental questions here is, are the small halos at small scale within the Milky Way just not there? Or are they there but non-luminous? And that is sort of the discriminating test between these different models of sort of high mass particle dark matter that we see here. So if there are lumps, then they should affect the tidal streams we see in the galaxy. This is a video of a model of a very kinematically cold stream that will interact in the lower panel with a couple of dark matter subhalos. And the frame of the movie is following the stream as it orbits around the galaxy, which is why it looks a little bit wiggly. And you can see that the impacts, as they're labeled here, create some density variations along this stream. You can also find variations in sort of the track, like the line that the stream follows, and in the velocity structure. So there's some tantalizing hints, including some work done by Adrian, who's sitting right over there, that we are seeing this happen in the galaxy. Gaia's role in this, by the way, so this is a particular tidal stream here, and you can see that there's some disturbances. And Gaia's role in this was to more efficiently than ever before remove interloper stars that are not members of the stream by making a selection on the proper motions. And that lets these disturbances show more clearly against this very thin stream. So the big question now is, if this is really what's happening here, what does it mean for our different models of dark matter? How often do we actually expect for a stream like this for this to happen? Are these impacts consistent with the types of halos we think are running into the streams at this distance from the center of the galaxy? And that's where, and that interpretation is where cosmological simulations come in again. And this is one of the very few ways that we know of to probe small scale structure in dark matter. And to show you how that's done, you can just make sort of a scaling argument for the degree of disruption S that a dark matter halo will have on a stream. And it's sensitive to the mass, but also to the scale radius of the perturber through the impact parameter. So dark matter halos are sort of are expected to have a sort of break in their density profiles, and the location of that break is the most effective radius at which they can scatter things. And so the impact parameter that is optimal for scattering is the scale, telling you about the scale radius of the perturber, which also scales with the mass. It's also telling you about the phase space distribution of both the tidal streams that are doing the probing and the dark matter subhalos, which is yet another handle that we have on what the dark matter is doing. The trouble is that unlike those clean examples that I just showed you, cosmological halos are pretty complicated, and probably the signatures are more complex than what you've seen on the previous slides. Even in a perfectly smooth galaxy with no substructure, a cold stream will experience nonlinear or resonant interactions that can create structure. And in a situation where you do have substructure in the halo, the disturbances can show up as gaps, but also they can show up as truncations of the stream, as thickening of the stream, as deviations in trajectory, and all these effects are superimposed together. Because if you follow a stream through the galaxy and mark when subhalos come close to it, you see that it's sort of being continually bombarded by substructures. So the vast majority of these interactions are really weak, but not all of them. And so we need to know sort of statistical expectations for what to expect the impact on the streams to be from this spectrum of interactions, since we see that many things are happening at once. All right, so another wrinkle is that the galactic disk is an efficient destroyer of substructure. And this is work by Jenna Samuel, who's a grad student at UC Davis. And what this plot is showing is, as a function of distance from the center of the galaxy, what fraction of the substructures should still be around compared to how many would be there if we didn't have a disk. And so in the inner part of the galaxy, the disk is depleting something like 80 or 90% of the structures that would be perturbing streams. But there's a very large scatter in this that just has to do with the particular details of the galaxy forming and the accretion history. So the most popular streams that people have used to look for the signatures of interactions with substructure are all in that region because they come from globular clusters, which are very dense collections of stars, and they make nice, bright, kinematically cold streams, but they have to get very close to the galactic disk before they get tidally disrupted. So you find them down here. At larger distances, you find less of this depletion going on, but out here you mostly get streams from satellite galaxies. Here's an example, and you can see they're less dense in terms of their stars. And so they provide different challenges for trying to detect the influence of substructures. And my group is trying to understand how we can use the ensemble of different streams from different types of progenitors to test the existence of substructure in the dark matter halo. So the subhalo distribution is a direct prediction of whatever DM dark matter model that you have. And the number and the distribution of the streams that you get from satellite galaxies is a secondary prediction of your dark matter model, because the dark matter controls what the mass profile and the central density of the small halos hosting the progenitors of the tidal streams is going to be. And that tells you how susceptible they are to being tidally disrupted. So there are a number of different levels at which the dark matter model will influence this process. The number of encounters that you get depends both on the phase-based distribution of the subhalos and of the streams. So the length and width of the stream is involved, and also its velocity dispersion, so the thickness of the stream in phase space. And then the masses of the subhalos and their distribution in the galaxy. And then some of these things are sort of cross terms between these two. So the relative velocities of the streams with the subhalos, for example, and the sorts of impact parameters that you expect. So what we've been trying to do in our group is test whether some of the typical assumptions people use to simplify that messy expression are actually played out in cosmologically simulated galaxies like the Milky Way. So one typical assumption like that is that the subhalo distribution is isotropic. So in any direction that you look, you expect the same radial profile. But instead, when we look in our simulations, we find that there's a slight preference for either polar or coplanar orbits with respect to the galactic disk, even at relatively large distances. And the distribution of scattering subhalos is not necessarily the same as the distribution either of present-day satellite galaxies or the progenitors of the things that are now tidal streams, which means that you can't use either of these populations necessarily to back out what you should be using instead of an isotropic distribution. This is work by my grad student, Nand, who is entering his 4th year. Another common assumption is that the relative velocity distribution of subhalos should be isotropic. And this is not really the case either, both because the disk preferentially depletes subhalos on radial orbits. So down here you can see this is as a function of their tangential velocity. So low tangential velocity means a radial orbit for the subhalo. And if you don't have the disk, you get these distributions with the dashed lines. And if you include the disk, you get the solid lines. So most of the stuff that disappears is on one type of orbit, which will change your expectations for the relative velocities. And also the streams themselves tend to prefer orbits that are coplanar with the disk. So teasing this out to sort of understand how it impacts the frequency with which we expect these interactions to happen and their power for disturbing the streams is a subject of our work right now. Incidentally, in testing all of these assumptions, we had to identify and characterize all these tidal streams in our cosmological simulations. And we've released the particle data publicly alongside the characteristic timescales for each stream's progenitor and our low order basis function expansion models for the galactic potentials. And we hope that this will provide a realistic test set to challenge different methods of modeling the Milky Way's mass and shape by modeling its streams. So the next step is going to be to get priors on the distribution of impactors for cold dark matter and then extend this to other models. The disk depletes some of the subhalos even at larger distances, and that'll probably calm things down and lessen the issue of all of these overlapping signals from all of these different interactions. But it's important to also note that the ability for a subhalo to disturb the stream is roughly flat across decades in mass. And this is both very powerful because it allows for sensitivity to even very small substructures, but also makes it more difficult to come up with good predictions because it challenges our ability to extend our simulations to high resolution. And you can see this from looking at this relationship or the scaling relation for the strength of an interaction. The number of it's proportional to the mass. The scale radius sort of goes like mass to the 1/3. So this is a little bit less than mass, but then the number of subhalos grows as mass goes down. And so if you put all of these scales together, you get something that's like m to the 2/3, nearly only weakly dependent on mass. All right, so I have gone over all of this stuff now, and I hope it's apparent to you that in all these areas, a big key to progress, and in the future, this is also going to be true, is that we need to confront our data and with our theories using realistic cosmological test cases. And so that's the reason why I've been working so hard on doing things like synthetically observing our simulations to create what Gaia would see if it observed our simulated galaxies. So this work was done for DR2. This is an example of one of our fake Gaia surveys of a simulated galaxy. And this stuff is all publicly available if you want to browse around. And our intent here was to create a system where the data model essentially looks like Gaia, so the same measurements that Gaia makes in its catalog, but with all the ancillary data and the underlying history of the galaxy and the true dark matter distribution all available so that, excuse me, so that you can use this type of realistic mock data to test models that often have very complex series of assumptions that go into them, and make sure that you're not at some point programming in the Milky Way as we know it into the model that you're trying to build to discover what we can't see yet. And this is work that I did with Sarah Loebman, who's in the audience right now, with Andrew Wetzel, who will be here next week, and Sanjeev Sharma, who couldn't make it. Coming very soon, and of interest for the people in my workshop particularly, is that we're upgrading these to Gaia DR3 error model. And we've also incorporated a model of the apogee chemical abundance uncertainties for the chemical abundances that we track in the simulation. And And if Ted is good to his word, at this workshop, we will also be able to convolve it with the apogee selection function using Ted Mackruth's modeling efforts there. And this work has been led by Farnek Nikaktar, who is also a grad student at Penn entering his 4th year. So we have now a lot of these kinds of realistic simulated data sets. And I'd like to end by pointing you to a place where you can find them all if you're interested in looking at this more. So this is our group's website. I am going to end on an ad, I'm sorry. Let's see if I can get this window over here. Interesting. No. I'm giving you another talk now. Great. Okay. Well, this isn't working. Here we go. Yeah, there we are. Sorry, live demo is always great. So if you go to the data tab, you'll see information about all the stuff that I talked about today and what to expect soon. So with that, I think I will leave you. It's always an exciting slide, but I'll leave you with these conclusions and take questions. Thanks very much for your attention.
Oh, thank you, thank you. I hope that's, oh, it's coming through with an echo. Okay, well, thank you, Robyn, for that wonderful talk. And I see the first, perhaps I should. Okay, the first question I'll take is from the G in GD1, who is Carl Gromeyer. So go ahead, Carl.
Thank you. Thanks, Robyn. That was a really beautiful presentation. I wondered about the Helmy stream. What was it that complicated the shape and mass of the galaxy using the Helmy stream?
Ah, right. So of the 4 that we used in that example, that's the only one that we consider to be phase mixed, in the sense that all the other 3 streams are still spatially coherent on the sky. The Helmy stream was discovered in the local solar neighborhood, essentially using a version of action space clustering. And it was also from probably a more massive thing than any of the other streams. So it has less overall power to constrain the potential because the fundamental size of its clump in action space is larger than for the others. So I think those 2 things are probably part of it. The other thing, my hunch is that it's probably pretty old because it's so phase mixed. And it may have, migrated from its original orbit quite a lot. So it may be telling us more about the assembly history of the galaxy than about its present day potential, but that's still sort of speculation. So.
Thank you. Okay.
Okay, thanks. Next, we'll have Dmitry Budko. Please ask your question.
Thank you so much. Very interesting talk. I wanted to ask you how does the new Gaia data, what does it tell us about the modified gravity pictures?
It's a very good question. That is a little out of my area of expertise. But let me think about that for a second. So one of the things that we can do with all this dynamics is to test whether or not dark matter could be a modification of gravity. And a lot of the challenges are going to be on the same lines as the bullet cluster, where we see evidence that the dark matter is moving in a very different way from the luminous matter. And so any model of modified gravity would have to account for the fact that we can have matter that is moving independently of the light distribution. It can't just be a rescaling of gravity to what we see. So especially the stuff with the dark matter wake in the LMC or perturbations that are caused by substructure and dark matter from non-luminous structures. Those things are in a global way, things that modified gravity theories would have to explain. beyond just, being able to reproduce the rotation curve of the galaxy.
Okay, thanks. I think next is Julio Navarro. Is it JFN? Is that you, Julio?
Yeah, that is me, Rosie. Thank you very much, and thanks, Robyn, for a wonderful summary of all the work you've been doing on this. My question is about the lumpiness part of your talk. I mean, many of us in the cold dark matter, similar community believe that there's always a remnant for, a cold dark matter halo because it has a cusp. As a cusp, this never gets disrupted, and the simulations at some point, fail to capture that, and you create numerical, dissolution of a halo. How much do you think you're missing by, trying to do these estimates of lumpiness using direct simulations, which are bound, if what I said before correct, which are bound to fail, right? So you'll be missing hundreds and hundreds of very small subhalos.
So, Julio, this is a good point. I think we can, in some sense, quantify some of what we're missing by doing convergence tests, as you know well. But I think beyond that, I think we got to look at whether or not these tiny things are really going to do a lot of damage to the distribution of tidal streams. I'd like to look into this more from an analytic perspective, actually, because my understanding is if you have if dark matter halos continue to follow sort of an NFW profile, then their scattering power is greatest at the scale radius. And once the scale radius gets too small, then the impact parameter that you'd have to have is within the stream and therefore not that effective. So I think it's worth asking, first of all, do you still expect these tiny leftover cusps to be that same profile? Do you expect something else? And second of all, what is their net impact? I think because the mass function is so steep, also the simulations are going to tell us more about individual interactions with tidal streams, and the kind of analytic analysis you can do to account for the cusps is likely to tell us more about how diffusive we expect those tiny interactions to be over time. But that's very, very much on my mind these days, and thanks for bringing it up.
Okay, thanks, Rob. I guess I worry, as you do, the fact that if there are so many low mass objects that we're missing, especially close to the center of the galaxy, and even going close to the disk of the galaxy, that we may be dominated by an effect that we cannot realistically measure directly in the simulations. But I take your point that we should look into this a bit more in detail. Thank you.
Thanks.
Okay, we have time for another question from Ilya Mandel.
Hi, Robyn. First of all, on behalf of this year's colloquium committee, thank you very much for starting us off with such a wonderful talk. It was a great pleasure to listen to. So maybe following up on the previous question, there have been ongoing suggestions that maybe there are some intermediate mass black holes floating around. People would dearly love to see them. My question is, can you place through these kinds of observations a constraint on their maximum mass, let's say, or their overall density, if such things do exist in the halo, let's say, 10,000 solar mass black holes floating around?
Yes, you can. So the fact that the main constraint just comes from the fact that we see tidal streams at all. So there can't be too many IMBHs out there. They're far more effective perturbers of streams than dark matter substructure is likely to be in most models that I know about, because they're essentially point masses instead of these sort of fluffy things. I remember that recently there was a paper on this. I think one of the authors was Jerry Oestreicher, because I used to argue with him about it when I was at Columbia. But if you come and talk to me later or send me an email, I will look up the reference for you, because I can't figure it off the top of my head. And it's been years since I read that paper, and we had a pandemic, so I don't remember what their conclusion was. But the other interesting thing is that when I way long ago did some estimates of this, the limits you could place were relatively weak, but that was before some recent developments in like the provenance of different kinds of black holes that you expect to be floating around. And so some of the mass ranges that were not considered probable back then have been like revived now. And so it's really worth another look, I think.
Thank you.
Let me just ask if there's any local questions.
So when you do all this work to cut down the simulations to what we actually observe, are there things you wish we were observing differently? Like you could change the observing strategy to make this constraint better?
Great. So the question from the room is, when we do synthetic observations of the simulations, are there things we wish that the observers were looking at differently or more or something to confront? As a theorist and a simulator, I tend to want to turn that question back on you and ask, you know, what should we be accounting for in our simulations that we're not doing? Actually, tomorrow's discussion, I'm going to come back to this point a lot, because I think it's really key to where we're headed with large surveys. Like, what do we need to be worried about in terms of selection functions and stuff like that, in terms of error models, and what doesn't really matter? And I think we need a lot more experience on that front in this game. On my end, I am like an addict of big data sets. And so the more the merrier for me. And I'm especially fascinated by the fact that the more dimensions of information we seem to get about Milky Way stars, the more information we get about them in like an information theory sense. Because there are correlations not only between the dynamical quantities associated with stars, but also, as is the subject of this workshop, the elemental abundances in the stars, their ages, their other parameters. I'm very excited by the development that is coming around to measure ages more precisely for large numbers of stars, because that's the thing that we actually simulate. And a lot of times we're stuck in this game of trying to back out the ages from this mess of chemical abundances. And for some problems, if we can just measure the ages directly, it allows us to eliminate this sort of middleman between what we see in the simulations and what you measure in the galaxy. So I'm really excited about that, which is part of why I'm here.
So indeed, I think the workshop is tying together ages, chemical abundances, motions, and we're really having a great time here. Well, thank you very much, Robyn, for your talk. I think we have to wrap up now and move our discussion to the patio. Sorry for all you people listening remotely. We're going to gather on campus, beautiful Aspen campus. Thank you again, Robyn. Let's thank Robyn.